Ishmael, your microphone is on. Yes, so we are going to look at probability theory, but we won't go deep into it. Obvious reasons we expect to look at certain issues, certain theory about statistics, but we cannot go through entire, probability. We can't go through the entire topic, but Ishmael, your microphone is on. When you put off your microphone. So one reason why this topic is important, because we are going to apply some probability theory in FEE522. And we expected to have looked at it by then. But of course, the other main one is that most of the signals we encounter in our communication systems are random, whether it's in the form of noise or even the desired signal. It will still be random to the receiver. Because the receiver does not know exactly what was sent by the transmitter. So it is random in that sense. That's why we will be trying to look for certain aspects in the randomness to be able to decode which signal it was. So so I've changed my configuration and I'm getting used to it. Yeah. So those are some of the notation we are going to encounter in this topic. The capital X, capital Y, we are going to encounter that quite a lot. We always use capital X and Y to represent a random variable. P with the brackets, so that will be probability of an event. So Px means probability of an event X. Py means probability of event Y. We're going to encounter this P sub X of X, and sometimes just P of X. That means, I've just said distribution, but actually that means, well, it's a distribution, but it's a PDF, probability density function. Yeah. We are going to encounter the joint distribution of X and Y. And then we are going to encounter also, we're going to meet F sub X of X. And this is the cumulative distribution of X. And that's the probability that X, the variable, takes the value equal or less than X, the value at a particular time. So we are going to meet expectation of X, that symbol, E of X. We are going to meet mu of x. That is the statistical mean. And of course, you're also going to meet small m, which I've not written here, small m of x, which is the time averaging mean or time average mean. That's normally the difference between mu x and mx, m sub x. Yeah. We are going to meet var of x, the big X, the capital X, which means the variance, and is also written as sigma sub x squared. Then there is also the variance of xy. When we talk of variance, we are talking about x, but when we are talking about two events, then we talk of covariance of x and y. So those are some of the terminologies you are going to meet. Only about that. The mouse is having some issues. So I think you are familiar with this. P of an event just means the number of favorable outcomes divided by number of all possible outcomes. When you draw a dice and the event is probably what is on top of that die, then you see the probability of that is a sixth, because there are six probability of each of any of that value being on top is a sixth, because there are six sides, and we are assuming all the sides are coming on top are equally likely. So the probability of that will be a sixth. So the event will be, and I think we better be careful about that, because sometimes if you look at this from the English definition, it appears like the event is drawing the die. Drawing the die is an experiment. The event is probably having a six on top. Yeah. So probability of A is assigned to an event A. It is a value. It will always be between, because the probability of having a 1, a 2, a 3, a 4, a 5, and 6, which is the sample space, is 1. So probability of having any other event, of course, will be between 0 and 1. Yeah. So if PA is close to 0, obviously it means it is very unlikely that the event A will occur. And when it's close to 1, it's very likely to occur. And when it is 1, it means it must occur. It will definitely occur. Yeah. Let me some people here. So sometimes you see me having gaps, because I use two screens. I have to keep on moving from one screen to the other. One where I have my presentation, the other one I have the Google Meet. Yeah. So these are more definitions in probability. Sample space is denoted with S with these color brackets. So there will be, for example, for the row of dice is 1, 2, 3, 4, 5, 6, because it means the sample space where the your event is what is on top. The sample space is 1, 2, 3, 4, 5, 6. Yeah, I think you have seen here the event might be that the number on top is an even number. Because number on top being an even number, it means either it is 2 or 4 or 6. So that probability, of course, is 3 over 6. Yeah. Those 2, 4, 6. So this is the event. So that will be 3, because the total number is 6, and that 2, 4, 6 will be 3. So that will be 3 over 6. We'll move a bit fast. I think this you can read on your own. The probability of it denoted PA. I think that is the thing that you have already said. So I think I'm using the. Sorry about that. This is not the correct document. These are not the document. Hope you can see what I'm presenting. I made some changes in the new document. That's why I thought that is not the correct document. Sorry about that. But I think the one I've sent you is this one. That's what the document is, a 2023 document. I did make some changes, and so I'll move very fast so that you can have a look at it. Those are axioms of probability. I'm sure in maths you have met that term axioms. It means actually things that we take to be true. Yeah, they're slightly different from the rules. Yeah, they're just taken to be true. You don't have to prove them. They are not theorems. They're just axioms. That is the PA. That is the probability of any event is greater or equal to 0. Yeah, that is the first axiom of probability. The second axiom is the probability of yes, Samuel.
I can't see your presentation.
Oh, you can't see my presentation. I think when I think I have to share. Oh, I have to share afresh. I thought when I change the document, to just I have to share it afresh. Sorry about that. Thanks someone for that. Yeah. I forgot, once you cancel the document, then you have to share afresh. So those are the three axioms of probability. P is equal to is equal or greater than 0. That is the probability of any event is either equal to 0 or something greater than 0. It looks obvious, but it's taken to be true. It cannot be negative. So the probability of the entire sample space happening is 1. Yeah, because it will be one or the other or the other or the other. So the probability is 1. Yeah. Then we are saying that if you have got a collection of events which are disjoint, which is another way of saying they are mutually exclusive, then it means the probability of A union A1 union A2 union A3 up to infinity, which is well, this can be OR. You can use OR. You can use union or OR. It's simply the summation of I is equal to 1 to infinity P AI. Well, it means if they are disjoint, then their probability is simply you simply add the probability of each. That is what this means in civil English language. So if you have got P, maybe the best is to give. If you are saying A and B are disjoint, which means P intersection B is equal to 0. They are disjoint, they don't intersect anywhere. Then P A union B, that is U or B is what do you call it? Is simply PA plus PB. That's what this means when you have A and B. Here I'm talking of A1, A2, A3 as the events. And here I'm giving the case whereby you have got just A and B. I think it is easy to understand when you're talking about 1, A2. And for a finite collection, of course, it is that is the summation of I is equal to 1 to N P of AI is infinite. This is when the collection is finite. I think we can move faster. These are rules. Rules, as I said, can be derived. So this is a computational probability, that is P A given B. That's what this means. Is simply P, A, and B, which divided by PB. And of course, P and B means all of them happening, not all. Yeah. And PA and B is simply PA given B times PB. All these can be proven. For independent events, of course, PA given B is just PA. They're independent. It means the occurrence, the probability of A happening has nothing to do with B. So PA given B is simply PA, and the probability of P given A is simply PB. Just means PB. Probability of B happening does not depend on A. We are going to see this becoming very important when we are doing information theory in second semester. And therefore, for independent events, it means PA given B is simply PA and B is simply PB and PA. You can deduce that from, again, you can derive that from all this. The addition rule is PA of B is simply P, and don't mistake this. Add means intersection, this means union. Because sometimes you may think union to mean and, yeah. But union is or, yeah. So PA, and of course it will be the union will be bigger or is bigger. The probability of this happening or this happening is normally higher than this happening, or maybe this happening and that happening will be probably higher than probability of this happening. Yeah. Compound events. What's a compound event? Is an event with two or more favorable outcomes. So they can be either mutually exclusive or mutually inclusive. So mutually exclusive compound event is when two events cannot occur at the same time. Like head or tail. Yeah. When you throw a coin, actually is either the head or tail. They cannot occur at the same time. Yeah. When you throw two coins, when you throw a coin, getting a one on top and getting a six, actually they are mutually exclusive because you cannot get a one and get a six. But if you throw two coins, the probability of getting a one on one and a one on the other, they are actually not mutually exclusive because they can happen. Yes, Samuel.
Yes, Gray is in the waiting room.
Oh, somebody is in the waiting room. Okay. Oh, yeah. Let me go to this. Thank you very much. Yeah, let's proceed. I hope there are no questions. This one you can read on your own. Disjoint and mutually exclusive events. They can be shown in a Venn diagram. This you could have done in set theory. We can continue independent events and later events. I think I've already said that. Conditional probability, I think I've already talked about it before, so we can just proceed. This is just an example of conditional probability. You can have a look at it at your time, but in this case, I think what is the question? The question is whether this is the question. Oh, the questions are here. So you are given these probabilities that Joe takes analog electronics is PA is equal to 0.4. Probability that he also takes power electronics, he takes 0.5. The probability that he will take analog electronics, given that he enrolled for power electronics, is 0.6. So the question is, compute the probability to enroll for both analog electronics and power electronics. And that is, I think, calculated here. We are saying that P A given B, P and B is PA given B times PB. And we have been given PA given B as 0.6, and this PB is 0.5, that is 0.3. And then the second question was calculate the probability to enroll in analog electronics or power electronics. That is PA or B. They're just using the rules of probability. That is 0.6. That question is, are the two events mutually exclusive? If they are mutually exclusive, it means P, A, and B is 0. Yeah. And P of B is 0.6. And the next question is, are they independent or independent events? P, A, and B is simply PB times PA. And it turns out they are not, because PB, we have found P, A, and B is that. So PB and PA is different, is 0.2, is 0.2. So no, because if there are independent events, this will be the same. This equation should prevail. It's good to understand there's a difference between independent events and mutually exclusive events. So is this Bayes theorem for independent events? Again, this we apply in our second semester. That is for independent events, P A given B. And you can understand why this A given B will be important, because we'll be talking about the output of a system given that the input is known. What is the probability of being this given that the input is known? Yeah, because the output will not be, is not known. Even if you know the impulse response, you don't know the output because of the noise. You don't know the probability of output being this. Yeah. Yeah. Why are we saying that? Of course, because if you are sending certain symbols, so you want to pick the symbol whose probability of occurrence is maximum. Yeah. Deducing from what you have received. Yeah. So it will be straightforward. If, for example, you have a noiseless channel, there's no noise, then you know that if you send this and there's no noise, this is what you're expecting to receive. But with the noise, that changes. So you can see why this is very important. This conditional probability is the fact that there is noise. So for sure, you cannot tell the symbol you're going to receive, even when you send a certain input. You can only be able to, you can only know the probability of it happening. So P A given P is probability of it. I think I've mentioned it. I'm repeating myself in my notes. So let's proceed. So I think nobody has problem with the basics of probability, for the reason that we have done it at one time at the university in high school. I think I used to teach this in high school many years ago when I left my high school. So probability distribution is a statistical function, I think we know what it is, that describes all the possible values and likelihoods that are random variable and take within a given range. These terms become clear as we move on, but we are saying that's what's a probability distribution. So it may just be some histogram or assigning every value to some probability. For example, if you draw a coin, so the probability distribution will be telling you will be giving you what you expect, the probability you expect of each of those outcomes. So mouse. So probability distribution, okay, and there are the probabilities. Yeah, probability distribution is a list of outcomes and their associated probabilities. That, of course, is in probably discrete probability distribution. It will be that will be a type of a probability distribution. Of course, for a continuous probability, that may not happen. A function that represents a discrete probability distribution is called those two terms. I hope you are familiar with those two terms. That we talk of probability mass function when it comes to a discrete probability distribution, and we talk of probability density function when it comes to continuous probability distribution. Sometimes there is confusion between the two. They mean the same thing in different domains. Common probability distribution. One is uniform distribution. That is referring to a statistical distribution in which all outcomes are equally likely. And sometimes we assume uniform distribution in communication to make our life a bit easy. Sometimes we are not even sure it's uniform, but sometimes we assume that probably a value will be between a certain space can be is equally likely to be any value between those two values. I think we are going to see, for example, when you're talking about how we apply probability distribution and cumulative probability distribution, we will look at the example of in sampling. I think when we reach there, I'll give you that example to make to clarify or to see why we are even learning this in the first place, why it's so important in communication. Bernoulli distribution, of course, is a single trial with only two outcomes. Example, flipping of a coin gives you a Bernoulli distribution. Binomial, this is actually a sequence of Bernoulli events where you throw, for example, a coin multiple times and then count the number of heads and tails. That will be binomial. Sometimes there is confusion between binomial and Bernoulli. This is a single trial with 12 cards. These are many trials where there are only two possible outcomes at each trial, but now you're looking at an event across many flips. A number distribution, I think you are familiar with this. So it will be a kind of a bell. Yeah, of course, this is a linear distribution with mean 0. You can have it either on the right or on the left. The mean can be, well, the mean will be positive, so it can be on the right. Yeah. Or it has to be, for it to be a normal distribution, it has to be symmetric around the mean. It has to be symmetrical around the mean. Yeah. So if the mean is here, it will be, if 0 is that. If it is mean is here, then it will be that. That's an inverted bell. So any questions so far? If I've said something that has contradicted what you have come across, sometimes that can be, but I hope not. So we are going to look at random processes, because that is area which is very important for us, especially, again, I'll mention noise, because noise is a random process. So knowing how to handle random processes is very important because it will tell us how to handle noise, how to be able to recover our signal in the presence of noise. Yeah. So a random process is a phenomenon that varies unpredictably as time goes on. And you should not mistake a random process with a random variable, because the process is a variable is just one incident, one experiment, one random experiment of that process. Yeah. For example, noise is a random process. But when you take the value of noise at a particular time, then that is a random variable. And that noise, yeah, so that's a random variable. So it can be part of the process. And you can take that either at different places at the same time, or it can be at different times, but you're dealing with the same process. Yeah. And that's how sometimes you have what we call, if you conduct different experiments on the same process, then you're going to have multiple random variables or the same process. Yeah. And you call that an ensemble. Yeah. So a random process is an ensemble of random variables such that is a collection of ensemble of random variables x of s comma t that are functions of a real variable of time t. Yeah. I think this will be sometimes the definitions are easiest. Oh, that will be a random process. Yeah. So you have event A, that's the same random process. Maybe this is at different places within the same system, but it can simply be at different times. So when you talk of this, we are talking of the start of your experiment. Yeah. And then we're talking about the start of this experiment. The start of the experiment. They don't have to be at the same time, but that is the start of the experiment. Yeah. So these are now random variables of a random process. Yeah. Where are we? So these are just terminologies that apply to random processes, how we classify random processes. It will depend on, of course, this state space S and the parameter T. In most cases, this T is time. It need not be time. I can't think of outright cases whereby it will be something else, but in most cases, this is time. And for sure, in our case, where we are dealing with noise, this parameter is T. Yeah, is time. Yeah. So if both are discrete, then we call that random process a discrete random sequence. Yeah. That is where they are discrete, then as a sequence. And the example will be the nth toss or fair die. That's a discrete random sequence. Yeah. So t is equal to 1, 2, and of course this is the number, and this will be the value of each. Yeah. The value at each throw. The other one is if t is discrete and s is continuous, we call this a continuous random sequence. Because you can see temperature at every nth hour. You are doing at every nth hour. So that is what is discrete. The temperature can be any value, therefore that is continuous. And this, since we are not talking about continuous, you're talking about every nth hour, then that is discrete. That would be a continuous random sequence. Temperature can take any value, but of course the time does not take any value. We are looking at every hour. If T is continuous and S is discrete, again this becomes a discrete random process. For example, the number of calls received in an interval 0 to T. So in this case, this interval can be, T can be anything between this interval, but the number of telephone calls is either 1, 2, 3, is not continuous. If both S and T are continuous, the random process is called a continuous random process. That's the maximum temperature in an interval. So this maximum can be anything, and also it can be talking about the interval can be anything. So this is what we call a continuous random process. So we're going to talk about a process, continuous random process, continuum random sequence. Yeah. So take note of those terms. Random variable, we have already talked about it. And what is it? It represents the functional relationship between a random event and a random number. Yeah, that is what we call a random variable. Yeah, and a real number. So it will be a random event, A, and a real number. So a random variable may be discrete or continuous. Then there is this term cumulative distribution function, is very important to us. We are going to look at an example of where we apply it in our area. So we use this capital F sub x of x to refer to cumulative distribution function. So for variable x, that one is simply means, for example, for a discrete random, variable. Well, no, it's for any variable actually. F sub x of x will be the probability of x of the value being equal to or less than x, where p x is the probability random is less than or equal to x. Yeah, that's okay. So the distribution function fx, the cumulative, sometimes the word cumulative is meant, but actually this is a cumulative, has the following properties. It will be between 0 and 1. If fx, that is, if it is for x1 is less than, if x1 is less than x2, then this applies. And obviously it applies because if we are talking about, let's say, the probability that let's say you have got, the easiest example would be if you are drawing 2 dice, for example. Yeah, if you are drawing 2 dice, it means one can be 1, 2, 3, 4, 5, 6, and the other one can be also be 1, 2, 3, 4, 5, 6. But let's say you're looking, your event, what you're interested in is the total. of what is on top of each die. Of course, the smallest can be 2, yeah. The smallest can be 2. Then of course it can be 3, and then there can be 4, 5. I don't know, a good example, 6, 7. But I think this will be a very easy example. 8, 9, 10, 11, 12. I think it can be any of those numbers. And if you look at the probability, you are looking at the number of times it can happen, from which you can judge the probability. So this can be, this is once. I think this is more of a histogram, but from it you can do to reduce the probabilities. This is, for it to be 3, either this and this and this and this. So 2. I think I've chosen a very good code. 4, it can be this and this, this and this, and this and this. So it can be 3. Yeah. 5. So 5 it can be what? 2 or 3. This. Actually, this would be 4. This and this should be. I hope everybody is able to see that. 3, 4, 6. 6 can be 3 and 3. Actually, they seem to be just 5. Just 5 times. 7, it will be 4 times. It can be that, not 7. It can be that, or that, and that. So that is 4 times. So it goes going down, yeah? So this will be here. Oh, this will be here. Sorry. This will be here. This will be here. Oh, 12 is supposed to be only 1. 10 should be 2. 9, yeah. 12 should be 1, sorry. So the maximum should be a 7, eh? 1, 2, 5, 6, 7. So 7 is, so is 4. This is 3. This is 2. I think I've messed up with the probabilities here. So I'm thinking 6 is the maximum. Maybe like 7 is the maximum. Oh, 6 should be the maximum. Oh. 6 can come from that, from that, from that, from that, from that. So it can be 6 times. Oh, 6 is 6 times. So 5 goes 5 times. 6 goes 1, 2. I've messed them up. But now, of course, from this, you can now be able to get the probabilities. And now if you draw the probabilities, you're going to find that, of course, this is a histogram. I don't think it will help us much. But what we are trying to say is, if the probability of, let's say, 2 now, the probability of 2, so maybe is 1 over, they are possible how many? They are possible 36. So it's 2 over 36. Yeah. These combinations can give us 36 possible outcomes. So one would be 2 over 36. So do some fraction there. 2, this will be 3 over 36. This will be another fraction. I think this is going to make this, maybe it will be here. That is for 2. And since there, 2 and 3 will be there, 4 will be there. Now we are talking about probability. This side is probability. Okay. So what we are saying is, if you are talking about cumulative, it will be something like this, because I've shown that there. So cumulative means being this value or less. So if you are talking about cumulative of this, then of course cumulative of this will be more than cumulative of this. Doesn't matter whether the probability is decreasing, but so long as you are talking about this one, it will be less than this, because we are talking about up to here. Now we are talking about up to here. So this is what we are trying to say here. Yeah. I hope I didn't take a lot of time explaining a very then cumulative distribution function of fx infinity is 0, negative infinity is 0, and positive infinity is 1. I'm stopping my mouse. So probability density of function, the relationship between cumulative distribution function and probability density function is here. Probability density function is given by that, yeah, and therefore here is given by that. Okay, so of course this is the what? I think I've gotten this mixed up. Oh yeah, of course, it means what we are saying is fx of x is equal to that. That's what we are saying here. I think I got mixed up somewhere. The way I've written here is not correct. So probability distribution function has these properties. Of course, is equal greater than 0, and we are saying from negative infinity to infinity, p of x, x is equal to 1. Yeah. Sometimes we use px for the probability density function. So let's be very clear about those terminologies. The cumulative distribution function, the probability density function for a continuous function, and probability mass function for a discrete function. That's the probability mass function. This, of course, will be represented by a table or some graph. This is for the discrete random variable. You don't have to spend time on that one, I think. This is what I was trying to generate. Actually, this is what I was trying to generate. Yeah, so it varies from 1/36. I think 2 can only happen once, 1/36, up to there is supposed to be a maximum of 7/36, and then it goes down to 1/36. Yeah, so 7, a total of 7 is the most likely outcome. Joint probability. So the joint probability, that is the joint CDF of x and y is given by that. The covariance of x and y is defined as this. This is the meaning of the covariance. When you have two variables, that is we have encountered this before, the expectation of x minus mu x, that's the mean of x, multiplied by y minus mu of y, and is given by that formula. We would get into derivation of this. Of course, you can derive this, but for now, we just take it as an axiom or as a rule which we don't have to prove. So two random variables x and y are independent if this is equal to this for every x or y. I think we talked about it before. When you're dealing with the probabilities, now you're seeing even with the probability based on the functions, this applies. This is conditional probability distribution for events A and B. The conditional probability is defined as that. I think we had looked at that before. And that those same formulas were applied for probability distribution function, for joint probability distribution functions. The same relationships. We deal with probability applied to the probability distribution functions when you have got for joint probability distribution functions. That's when you have two variables. So random process can be seen as a function of two variables. Why is this slide looking familiar? So the event, I think for our case, we are narrowing down to where the second variable is time. So for a specific event AJ, I think that's what we have done here. So you have got these different random variables of the same process. And one of the important things is to understand that when we talk about the all the processes, we are saying that you can get the mean of this by just considering a particular time and then looking at all the processes. And of course, we call that the statistical mean, yeah, the mu x. We are saying we are looking at the statistical mean across the ensemble. So it's the ensemble average or the ensemble mean or the statistical mean. And why for us certain properties are very important is because sometimes you don't want to do an infinite, because as the number of events tend to infinity, you can be able to work out the, what do you call it? I think we need to look at certain definitions which will give us the difference between the two. So we are saying to be able to get the mean accurately, this need to tend to go towards infinity. There has to be as large as possible to make that conclusion about the mean. And that's central tendency. Because whenever you talk about the mean, you're talking about central tendency. They tend to converge to a particular value. But that depends on, you have to do very many experiments. So you find that sometimes the processes which we are going to have a look at, where you can be able to conclude to get the statistical mean from the time average. Time average mean as one process tends to infinity. Yeah, that's what they call time average. If you can be able to deal with the process, I mean, you will want to deal with the processes whereby the time average, where the statistical mean can be deduced from the time average mean. Yeah, is a class of processes we are going to look at the ergodic processes. Yeah. So take note of those two because they keep on coming up when you're dealing with the processes in telecommunication. That we don't or rather we can say we are lucky in communication because this noise process, which is random, has those properties. It is stationary and also ergodic. Yeah. And simply ergodic means simply the statistical mean is the same as the time average mean. Yeah, just explanations. So statistical averages for a random process, value of a random process of course is unknown. So the distribution is known. So the probability density function is known. So mean of a random process is described as the expectation of x, and is defined is divided for a continuous process is simply the x of it is the integration from negative infinity to infinity of x multiplied by the probability density function. That is for a continuous random process. And this we are talking about is a PDF over the ensemble of events at TK. What do you mean? That's what we are talking about at TK. I think at some particular time. Yeah. Yeah. So we are saying if you look at the ensemble of events, then that's what we are talking about, Px of k here. It is not across there. It's not, you're not looking at a single event. You are looking at the entire ensemble. Yeah. So autocorrelation function is given by this, and is defined. Just 1 second. 1 second. Just 1 second. We can continue. The autocorrelation function which you were talking about the other day is given by this Rx T1 of T2, T1 comma T2 is given by the expression of x T1, x of T1 times x of T2. This just means times x of T2. Where x of T1 and x of T2 are just random variables obtained by observing xt at times T1 and T2. Yeah, that's what you are saying. Observing at this particular time and observing again at this particular time. Observing the entire ensemble at this particular time and observing the tail symbol at this particular time. I think we have already talked about this. The localization is a measure of the degree to which two samples of the same random process are related. Moments of a random variables. Again, I'm sure you are familiar with the moments and the central moments. So the moments, the first moment, of course, this formula applies. Yeah, we talked about the mean, but this apply for all the moments. Yeah, for the mean, n is equal to 1. Yeah, that's why you say for the mean expectation of x. And sometimes you can use the square brackets or the curls, the curly brackets. This is given by that x dx dx. Yeah. So the most important moments are the first and second moment. Of course, the first moment is the mean when n is equal to 1, and when n is equal to 2, it gives us the mean square value, yeah, which is this. Yeah. When n is equal to 2, of course, it gives us the mean square value, p of x squared. Yeah. I hope everybody is clear with this. I'm moving very fast. Again, assuming that you have come across it. And these future calculations will be based on this. The mean, all the things you're going to do, especially what is remaining, will be dependent on this. The mean, there's a conservation function, the mean square value, and the square of the mean. Yeah. Central moments. The central moments are the moments of the difference between x and the mean. Yeah. So the second moment is what is important to us. I think the first central moment is the variance. Yeah. It's not the variance. That should be actually the standard deviation. But of course, we know the standard deviation is the square root of the variance. So we don't bother with the first moment. Yeah. The second moment, the second central moment, I mean, the second central moment is called the variance. So by x is expectation of x minus mu x squared, because that is the central moment, x minus mu x, the difference between that. So the central moment is given by that. So the var x is given by that. Some of these formulas you can derive, but I said you won't derive them. You can go look at the derivations, and the derivations, they are lengthy. One derivation should take maybe about an hour. But for us, we don't need to derive them. For your understanding, you can go ahead and look for the derivations. They are in textbooks, but we will go through that. So var x, sometimes it's noted by that. I talked about that. And of course, its square root is the deviation of x. And variance is the randomness, measure the randomness of random variable x. Relationship between mean and variance. Of course, the variance, just by definition, is that, because you simply, we just opened it up. It is x minus ux squared. Also, it is the expectation of that, which of course becomes the expectation of x squared minus 2 mu x of x plus mu x squared. Just use the square brackets. Oh, I should be consistent. Either use the same brackets or curly brackets. So this becomes expectation. You can separate this because this becomes expectation of x squared minus expectation of 2. Oh, yeah, okay. This is the expectation of mu x squared. Of course, the expectation of mu x squared, the expectation of a constant is a constant because we are saying mu x is supposed to be a constant for the process we're dealing with. Yeah, W S stationary uh, uh, for stationary processes. Of course, mu x is of interest. When you have positive minus this 2 mu x, you can put it outside because so this is simply 2 mu x expectation of x. Expectation of x plus expectation of mu x squared. So this simply expectation of x squared. So I skipped those calculations. So this becomes simply this. So the variance is equal to the difference between the mean square value and the square of the mean. Yeah, that's the square of the mean and that's the mean square value. So actually the variance is the difference between the mean square value and the square of the mean. Expectation and variance of a discrete random process. You just replace the integration with the summation, and the same applies for that. Stationarity, a term you're going to hear a lot when it comes to communication. A random process is stated to be stationary in the strict sense if none of the statistics are shifted by a shift in the time origin. There are many other statistics which you're not going to look at, like skewness and all that. But if all those don't change with changing time here, then we say that is a stationary process. Yeah, shift in the time origin. Yeah, but we'll be dealing mainly with the ones which are just wide stationary. That is where two of the statistics, mean and causation functions, do not vary with time. So we say a random process is wide stationary if its mean and autocorrelation function do not vary with time. And of course, what happens, some of the questions you can get is to say whether a process is a WSS by calculating the mean and the correlation and establishing that they don't have the time, they don't have T. If you get either a constant, or it means that is a wide sense stationary. So ordinarily we're not going to look at strict stationarity, we just begin with the wide sense stationarity, where we are only concerned about these two statistics, the mean and the autocorrelation. So a random process is wide stationary if this is a constant, mx, does not vary with time. And this one does not depend on the time, it only depends on the time difference. Yeah. It's not constant, but just depends on time difference, depends on tau, time difference. Yeah. Then we say that process is wide sense stationary. These are some of the examples we are going to do when you come back. I remember you say that I just want us to complete the syllabus, then when you come back, we go through examples in various topics, which will be also form part of revision. Yeah. Autocorrelation function over WSS. Yeah, I think we can, if we cover the full 2 hours, I'm going to finish this topic. One of the reasons I also want us to have completed the topics is that during your long holiday, I think you have 4 weeks, you can be able to read for the exam, because once you come back, you have only 1 week. So autocorrelation of a wide sense stationary process. The autocorrelation is only a function of the time difference, tau, t1 minus t2. So Rx of tau is simply expectation of x of t times x of t plus tau. For tau, going from negative infinity to positive infinity. So for zero mean WSS, Rx tau indicates the extent to which the random values of the process raised by t are statistically correlated. I think this only matters when for a zero mean wide sense stationary. So these are the properties of a wide sense stationary process, that the Rx of tau is equal to Rx of minus tau. That is, the autocorrelation function is symmetrical in tau about 0. Yeah. Rx of tau is equal or less than the Rx of 0 for maximum. So we are saying maximum value of this occurs at tau is equal to 0. Yeah. We have seen this before. We even did an example, we found that the maximum occurs at tau is equal to 0. That is when there's no, when you're looking at the T1 is equal to T2. Yeah. So Rx of tau, this is how they are related, is that the GXF, G sub XF, which is the power spectral density. Sometimes you use G, sometimes you use S. So don't be confused when you say, in our notes, you might see them used interchangeably. In fact, in the next topic, we'll be using S. So This is a Fourier transform of tau. Yeah, that's why I say there are Fourier transform there. And Rx of 0 is equal to, that's the value of the at the origin is equal to the average power of the signal. I think we mentioned this when we are looking at autocorrelation, yeah, and cross correlation. We see that the value of the origin is equal to the average power of the signal. Again, this can be derived. You will derive it, but this can be derived. It can be actually shown that this is equal to this. Yeah. Again, it's a lengthy derivation. Yeah. So for your understanding, you can go through it, but for us, we will not ask you to go through it. So we don't. Its derivation is beyond the scope of this particular course. And sometimes when it says beyond the scope, we don't say you can't understand, but what is expected to be covered in this unit. But not that because you can't understand it, I'm sure it's within your scope. Yeah. Time averaging and ergodicity. And I've talked about it because we are saying ideally we like to know the statistical mean, because all those things we are talking about, all those properties we have been talking about are applying to a process. So the moment you want to find the mean and the correlation of a process, it would mean that you'd have to do what? You'd have to, for example, if you want to get the mean of the process, let's say mu. I want to look at this. This one normally I see out of confusion with the students when it comes to. Oh, sorry, yeah. Yeah, here we are. That is, you can see ux of t, some t1, or let's say just t1, defining at a particular time when this t1, yeah, this will give us the limit as n tends to infinity 1 over n summation of n is equal to 1 to n x, the capital X, of T1. Actually, if you look at this equation, of course, ux as T1, since we are talking about we are talking about a process whose mean is not changing with the time. So ut1 will be the same as ut2, ut3, whatever time it is you take. This will apply. But what we are saying is, go back here. We are talking about, you are taking the average of this. Yeah? You are taking the average of these values. Yeah? As n tends to infinity. So the mu of x is at n tends to infinity. So n will be this. So this will be n. Yeah, this is the n. So n will be this. Yeah. So at n tends to infinity. So for a very small n, for example, if you are only taking the three processes, that may not be very accurate. But as the number becomes large, the law, the central tendency, the law of large numbers applies. So we are going to get it accurate. Yeah. Where were we? We were where we were here. Yes. So that is the mean. But we are saying for an ergodic process, this statistical mean should be equal to this time average mean. Yeah. And the time average mean, again, you cannot take that within a short time and make a conclusion. So again, is that t takes tend to infinity. You have to take it over a large time. Yeah. Sorry. Just give me a second. Where is it? So, this time average, you are taking it over also a long time. So that's why you're seeing unlimited as t tends to infinity. 1 over t minus t over 2 to t over 2 x of t dt. So this for a continuous random process. So you can use it to get mx. And for a ergodic process, mx is equal to x. So again, some of the questions you can be asked is whether to establish whether a process is ergodic, which means they're expected to do this evaluation and show that if you do this evaluation or do this evaluation, the figure is the same. Say a constant or is zero and is the same. Yeah. And so we use the word is ergodic in the mean or ergodic in the autocorrelation function. So it is ergodic in the autocorrelation function if this applies. So if this applies, yeah, or rather we are saying this applies, this ux is equal to this, yeah, should be ergodic in the mean. Yeah, that's what we are saying, yeah. So because this is this, but you're saying if this is equal to this, then of course it's ergodic in the mean and it's ergodic in the autocorrelation. Ergodic for ergodic, oh yeah, for ergodic process, these are the properties of an ergodic process. That is mu of x is equal to the DC level of the signal. The mean simply means the DC level of the signal. If that signal is a random signal, it's a random ergodic signal, yeah, or is an ergodic random signal. mu of x squared is equal to the normalized power in the DC component, yeah. Normalized power, again, let's understand normalized power. It means where you are considering R equal to 1. Yeah, that's the normalized power. The number power is equal to I squared R or V squared over R. So when R is equal to 1, is what we call the normalized power. Second moment, that is the expectation of the of x squared, yeah, or the mean square value is equal to the total power. Yeah, and this quantity expected the square root. This means this of this expectation is equal to the RMS voltage of current signal, because we are talking about R is equal to 1. So we are talking about the mean, the RMS of the voltage and or the signal. If the process has zero mean, if it's ergodic and has zero mean, because ergodic doesn't mean it has to have zero mean, then the variance is equal to the mean square value. Of course, it makes sense because of this. You had it here, because of here. If this is 0, the variance is simply equal to the mean square value. Yeah. And it represents what? The power in the normalized load. The variance represents the power in the normalized load if the process has zero mean. And you understand the process of the zero mean? We are talking about a kind of process with zero mean. Yeah. Because without normal distribution and zero mean. Yeah. The standard deviation sigma sub x is the RMS value of the AC component of the signal, and if the mean is 0, then sigma of x becomes the RMS. You can see the difference. Again, it's good to be to get these terms correctly. So if it is this, then it is the AC component of the signal. But if this mean is 0, then this becomes the RMS value of the signal. The spectral density, we have mentioned it before, but I think what I've talked about mainly is the power spectral density, where we have said that the power spectral density of noise is a constant across the entire spectrum. That's why we call it white noise. Yeah, because of that power spectral density. So the spectral density, you can have the energy spectral density. The difference, of course, between the power and the density is one, of course, you divide with the time. So the energy spectral density is the limit at t tends to infinity of this, which is simply the same as infinity to infinity x squared of t dt. Using Parseval theorem, it can be expressed that you can use Parseval theorem and you can find that it is also the same as the square of the Fourier transform of this function. Yeah, that's why the x, the magnitude. I think again this can be proved. Yeah, it can be shown. You can actually do the derivation, but just suffices to remember it. Again, it's a lengthy derivation. Yeah, where x of f is the is the ft of the non-periodic signal xt. And we are saying if we call this if we let this be the energy spectral density, we are saying, oh, what is this? Oh, the total energy, this is the total energy. So we are saying if we let this be the spectral density, then the total energy is simply, and of course it makes sense, because the spectral density, when you talk of the density, spectral, we are talking of per Hertz. So to get the total energy, we are talking of energy per Hertz. So to get the total energy, you have to integrate across the entire frequency spectrum. We are saying we are plotting against the power spectral density. So if you have this, I of x, f, and we have f, then we simply just, it is taking this in the name. Just area under the curve, just integrate this. Will give you the total energy. Yeah. Oh, actually, it's area is the area under the curve of phi xf versus frequency curve. Yeah, is that? That's it. The power spectral density, of course, is the same, but now we are dividing with the time. So you have 1 over t. That is the difference between this. The average power of a signal is simply dividing by t. So if xt is periodic, in the period t naught, the signal is classified as a power signal. And Passivhaus theorem, yeah, now again we can show this, that the total energy is simply the magnitude squared of the what? The spectral components, the value of the spectral components. Because here we are dealing with spectral components. You can see we are talking about n is equal to minus infinity to infinity. When you see this summation, that means it's a discrete signal, but it means when you talk about the spectral components at particular values. Yeah. So that is so px is simply that as a summation of this. So these are the complex, these are the coefficients. Actually, these are the coefficients for the periodic signal from the Fourier transform. And the power spectral density GXF is equal to this. And for non-periodic signal, this applies. Don't worry much about this. You don't have to worry about this. We have not derived them, but also don't worry about this much. You stick more to the non-periodic signal, another periodic signal. So power spectral density or random process. So it has these properties that it is always greater than 0, it's always 0 valued. And again, TXF, that's the power spectral density, is symmetrical on the f axis. To be symmetrical, that's what this means. And this relationship, we have already talked about it, as the power spectral density is related to the autocorrelation function. And again, this is not, we should use tau with the autocorrelation function all the time. So gx of, g sub x of f and Rx of tau, they are a transform pair. That would mean you can also get this by finding the Fourier transform, or rather of the inverse Fourier transform of this. That's what it means. When you see something as transform pair, it means you can get the Fourier transform of this to get this, or you can do the inverse of this like this. And of course, the power already we have mentioned, that is simply integrating or getting the area under the curve of GXF and EF. That's the power spectral density. It's just like the energy spectral density, where you're dealing with the area under the curve for this. Now for power spectral density, is the same. The total power is simply that. We still have 10 minutes. Is there any question? Is there any question on what we have covered with the random processes? Because this is what we are likely in this semester. This is what we are likely to do. We are not likely to look at the probability. Probability, I only put it there because of next semester. We are not expected to cover it in the next semester. We are expected to just to apply it. Assume that we have dealt with it before. Otherwise, here we concentrate more on the random processes. Yeah. And I thought of looking at this first because it's going to come up in the next topic. We are going to deal with the match filter. So we are going to be using the same terminologies. And I just wanted to verify, or rather to clarify, not to verify. I can get that. And probably have done it in another unit when you have, let me see, make sure I can access that. And I just spent 5 minutes on it to give you a better view of application of this. I hope you can see that document. This document is from somewhere different, but it gives. Can everybody see that document where we are trying to get the signal to quantization ratio? And I like this example because everybody can see that, I hope. Very good, very good. So we use this to try to find out the noise power because we want to get this very important signal to quantization ratio. And to get it, you need to get the power. Power of the signal is straightforward, but power of the noise, we can only use is statistics. And what we are saying is quantization error, Q, is a random variable varying between plus delta over 2 and plus and minus. What actually this means is when you quantize, I'm taking you back to something probably we did. When you sample and then quantize, we all know what quantize means. It means probably for values between here and here, you are taking it to be this one. So when you're talking of delta, we are talking about this. So we are saying, you see, this value, the value of your signal is given by some, let's say you're using 16 levels. You're given by some combination of zeros and ones. And this represents this value, because that's what quantization means. It means any value between here and here is considered to be this value. So maybe when you get this, as the receiver, you see as the receiver what you're getting is this. And then you want to know what value was that. So it will be some value, it will be giving you this value. But remember, at the transmitter, that value could have been here, 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 here. It could have been anything. It could have been anything between here. But anything between here, because of quantization, was taken to be here. So what is the error? The error can be anything between here. So it can vary from negative, this, and the positive, this. It can be anything. So because if your value is this one exactly, if that was what was sent, if that was your original analog value, then there is no error. But it can be maximum this or this. So it can be anywhere between this. That's why you were saying is an uniform distribution. It can be anywhere. The probability of it being anything between here is the same. That's why we assume it's a random. I mean, it's a uniform distribution. That's what we are saying by uniform distribution. So that's why we are saying this f of q of the quantization of noise, it varies between that and that. So that is q, and this is the probability of q. So we're moving from minus delta over 2 plus delta over 2. Yeah. And we want to use that formula, that this total, which is a distribution function, the total is simply x fx. Yeah. Oh, what do we want to use here? We want to use this. We want to use, in fact, our interest is the ex squared. Yeah, this one. It's simply this. That's the formula we want to use. It's not the mean. We are not interested in the mean. Fx dx. And that is expectation of x squared is equal to that. That's what we want to use. But what we want to get is what is f of q. But f of q, since there's a uniform distribution, and this must be equal to 1, yeah, then it means this is 1 over delta. F of q is 1 over delta. So when we apply this formula, we are going to say the power to signal quantization ratio is simply x squared. So it is q squared fx, which is 1 over delta, which is fq here, 1 over delta. Yeah. Dx. So in our case is dq. Yeah. So you can see this is one of the application when you're trying to get what is the signal to quantization ratio when you convert a signal, because it is important. That one, not even the noise that you get as your signal is traveling. We're talking about the noise you get just by quantizing, not even by sampling, by quantizing. And you have to quantize, because if you don't quantize, you have too many values in between. Yeah. So, and we see that the power of this is simply you apply that formula, and of course you're going to get it as pi squared, delta squared over 12. And that's what we use now to find the PQN, of course. For the, now here we are simply saying we want to express the power of the signal as We want to replace the power of the signal as this. We are trying to bring in, like this. We are trying to express this delta as we want to bring n. Why are we bringing n? What is n? N is the number of digits. Is a number of digits that represent your signal, these ones. So in this case, n is 4. And actually what we are trying to say is the power, and it makes sense intuitively, yeah? The P, how do you know the P? SQ, not P. SQ and R. That's why you are bringing this, you are using this formula here. That is L is the number of levels, because this will depend on the number of levels. So if you have more levels, then this will be smaller. Less levels, this is bigger. More levels, this is smaller. So we want to show that the number of levels, which depends on the number of digits you are going to use to represent each level, is actually very relevant when it comes to SQ and R. And it makes sense. If you have very few levels, which means you are representing each level with very few bits, then you have a lot of signal to quantization ratio. And it comes out here, yeah? Because you can see SQLR actually depends on this n. If you do the logarithms, this is what you get. It's directly proportional to the n. You can see this n here. Directly proportional to the n. Yeah? You have more n, you have a better power PS, signal to quantization noise ratio. We want a bigger figure. With signal to noise ratio, we want a bigger figure. So more, then it means you have a bigger figure. It means noise is much less. Yes? Somebody ask a question. Somebody put up a hand. Oh, I assume it was there. Anyway, I introduced this just for the purposes of showing that exactly why do we look at this. This is one of the areas where you apply that formula. Whether you apply the formulas relating to probability of random processes. Yeah. And actually, in most cases, it's just applied with noise. Even in the last topic, we are going to see that it comes up when you're trying to detect your signal in the presence of noise. So I've kept you for 2 hours, but I think it is worth it because we are trying to finish the topic